Morning class. This is the last of the 3 screencasts on chapter 10 and it deals with the area of vapor pressure and changes in state. This is an area that comes up every year in the multiple choice section of the exam, and so it is an area that it's worth focusing upon. The bigger area from this chapter was the first area, which was intermolecular forces and also as that related to bonding. But this is also a big area that comes up frequently. So the idea is that a liquid evaporates. If you put it in a sealed container, then eventually it'll reach a point where that vapor is reaches an equilibrium state. So the vapor returns to liquid at the same rate that the liquid goes into the vapor. Okay, so the rate of evaporation remains constant, but the rate of condensation gradually increases until they reach equilibrium. Now this ties into the whole idea of Maxwell-Boltzmann distribution again. And this is where I do give you that worksheet to work on. If you may have seen it before earlier in the year, but I would like you to submit it at this stage, because what happens is that you've got this idea that at any given temperature there will be a certain number of particles that have the amount of energy needed to overcome the intermolecular forces of the liquid. And what happens obviously at a higher temperature, there are more particles moving at that temperature, at that speed, that have that kinetic energy and can overcome it. If you look at different the different chemicals, such as in this case a pure vacuum involving mercury, water, ethanol, and I think this is ether. You can see that each of these, the ether, has a much higher vapor pressure, so therefore will drive the column down. So what happens is that we take mercury, 760 torr, is the amount of the height to which mercury will rise in a vacuum. Now just going back to this for a second, within the Boltzmann distribution, we've got the concept that actually the particles that are at the surface have less forces holding them there. So it is easier for a particle to evaporate from the surface of a liquid than it is for a particle to boil from the middle of a particle, or to evaporate from the middle of the liquid. So what happens is the surface area is more likely to lead to evaporation. So if you take a liquid and spread it over a large surface area, it will evaporate much more quickly. So the relationship between different liquids at different and their boiling points. You can see here that diethyl ether will boil at about 30 to round about 30 something degrees. What happens is that ethanol boils at about 70 something degrees and 78.4 degrees, and water boils at 100 degrees. So what it is that we need to have a clear understanding of what boiling really is. What happens is boiling is the point at which the vapor pressure equals atmospheric pressure. So for a liquid, if it's in an open container, then it will continue to evaporate. But if you heat it, eventually the pressure at which it is condensing overcomes the atmospheric pressure. So the pressure inside the liquid is greater than the atmospheric pressure pushing it back into the liquid or keeping it in the liquid. At that point, the liquid can vaporize from anywhere within the liquid. Now for water, this is at 760 degrees, 1 atmosphere pressure. This happens at 100 degrees Celsius. So, because this is a relationship of boiling point to vapor pressure, this explains why if you're sitting at the top of Mount Everest, your water boils at 70 degrees, whereas if you're sitting in Hong Kong at sea level, the water boils at 100 degrees. We used to live in at the top of a major hill, about 6,000 feet in India, and our water boiled at about 92 degrees. So the boiling temperature depends upon the height, because the atmospheric pressure at that height is much lower, and therefore it's much easier for the molecules to move into the vaporous state. Okay, now the next part of this is the idea of phase changes from solid to liquid to gas. So when we move from solid to liquid, it's called melting, and the heat involved is called the heat of fusion, delta H FUS. Boiling, when we move from a liquid to a gas, it's called the heat of vaporization. And sublimation is when it goes directly from a solid to a gas. So here is a normal heating curve, and you will see questions like this in AP multiple choice. So the idea is that the temperature overall rises, but it stops when melting is occurring and when boiling is occurring, because it's overcoming those intermolecular forces which are holding them in that state. This is a different type of phase diagram. This is the one for water. And so you can see here, it's the interrelationship between solid, liquid, and gas. The thing that is interesting with water is the solid-liquid line goes backwards. All other chemicals, the line goes forward. What this means is that a solid, water, i.e. ice, is less dense than liquid water, which is why ice floats and life on Earth as we know it occurs, because what will happen is during the ice ages, life continued under the ocean. During the winter, life continues under the pond. There is a triple point here, which is where the solid, liquid, and gas all come together. So all three states can occur at that particular temperature and pressure. Now you can see for a normal chemical, such as CO2, that the solid liquid line moves forward. But there is these triple point. There's still a point where all three phases can occur. And you can see that there is a place at a low enough pressure where it can move directly from a solid to a gas. So this is called sublimation, and here is a piece of dry ice which is subliming. So thank you for listening to me. This what will happen is tomorrow we will be doing a quiz on this particular chapter.